Welcome to Digital Electronics Laboratory. So today in this video, we are going to implement another experiment. And the objective of this experiment is to implement a 4-bit binary ripple counter and observe its counting sequence. So first of all, we need to understand what is this counter. So you can see this definition of the counter. So counter is a register that goes through a prescribed sequence of states upon the application of input clock pulses. So what does it mean? So first of all, try to understand, suppose if we have a counter circuit, which is uh, fabricated out of the D flip-flop. Here you can see that we are having the D flip-flop. So normally this D flip-flop will be having a certain input pins. Generally, it is having just one input pin, and there will be two complementary outputs. So here you can see that these are the outputs that we have marked as QA, QB, QC, and QD. So let us suppose that when we are applying a certain clock pulses, okay, at this particular clock input of this particular counter, then this counter will go through a certain state, okay, sequence of states. So that you can see here, okay, in this picture diagram. So here you can see that this is our state diagram you can see. So let us suppose that this particular flip-flop is starting at 0000, okay, and then when we having the next clock pulse, it will be going to this particular state, okay. Similarly, it is again when the next clock pulse will arrive, it will be going to this particular state 0010. Okay, so this way actually it is going through a particular sequence of states when we are applying the next and next clock pulses. Okay, so this way actually counter is able to go through a certain counting sequence, right? So now we have to see this counters can be a synchronous counter or it can be a asynchronous counter. So what does it mean by a synchronous counter? So normally, if we are considering this example, here you can see in this particular circuit, so here you can see all the flip-flops are actually having a common clock, okay, common clock input. So whenever you are applying the same clock pulse to each and every flip-flop, okay, if the flip-flops clock input is actually connected to the same clock pulse, then it is called as the synchronous circuit or synchronous counter, okay. And here again you can see in this particular case it is your asynchronous counter, okay. So here what is happening is here you can see the only first flip-flop is actually connected to a particular clock, okay, and the other flip-flops that you can see in the subsequent stages, okay, like flip-flop number 1, 2, and 3, here you can see that it is not connected to the same clock, but rather you can see that one of the output of your first flip-flop, okay, is driving the second flip-flop, okay. So here you can see that this Q bar is actually connected to the clock input of your second flip-flop. Similarly, the third flip-flop is actually driving by the output of your second flip-flop, and so on, okay, that you can see from this particular picture. Normally what is happening in the synchronous counter, all the flip-flops will be receiving the same clock common input, okay, and here it is actually receiving a different clocks, okay. One more thing that you can observe is that normally in the synchronous counter, the state of all flip-flops will make transitions as soon as we apply the clock pulses, okay. So all the state transitions of the flip-flops will happen simultaneously, that you have to remember. But in this case, it is not necessary that the transition of all the clock all the flip-flop will happen simultaneously. It may happens one by one, okay, that we have to understand. Fine. So normally if we want to implement a counter circuit, we have to use the flip-flops, okay. It can be a RS flip-flop, which is known as reset set flip-flop, or it can be a D flip-flop, it can be a JK flip-flop. So today we are going to observe this particular flip-flop, means we have to implement this 4-bit binary ripple counter, okay, which is a class of asynchronous counter, okay. So that we are going to implement, and that I am going to implement by using the this particular D flip-flop or JK flip-flop. So that we have to use. Fine. So here we can see that in the binary ripple counter, you can see normally in this binary ripple counter, either we can use this D flip-flop or we can use this JK flip-flop. Okay. So in this case, first of all, you have to know what will be the function table of your D flip-flop. Okay, how it actually works. So I have already made the videos onto this particular JK flip-flop and D flip-flop that you can go through how it functions. Okay. So here you can see that whenever we are using the JK flip-flop to implementing the binary counter, okay, 4-bit triple binary counter, okay, that time it should be operated in the toggle mode. Okay, so whenever this J and K input is connected to bit 1, okay, then it will be acting as a toggle mode. So what does it mean by the toggle mode? Means when it is connected to 1, and let us suppose that the output is at present is Q equals to 0. So when the next clock pulse will arrive to this particular JK flip-flop, that time the output will be complemented. That means that if it is initially 0, then it will become 1. Then again at the next clock pulse, again this 1 will be complemented and the output will become 0. So that way it will work. Okay, so that you have to remember, it will be acting in a toggle mode. All this JK flip-flop, you can see all the JK flip-flops are actually connected to 1. Okay, it is connected to positive supply, means it is connected to logic level 1. So that way we have to make connection. Here you can see in this D flip-flop, okay, when we are making the counter using the D flip-flop, here you can see in this case we are actually, here you can see this is the clock input, okay, and we are actually, this triangle represents that this particular D flip-flop is your positive edge triggered. Okay, and similarly here you can see that we are having the triangle, but before this triangle we are having this circle that represents that this JK flip-flop that we are using is our negative triggered flip-flop. Okay, so here you can see this particular connection. This connection we have to implement. Okay, and then we have to observe the output sequence, right? So here you can see in this case of counter circuit using the D flip-flop. Okay, so first we need to apply certain, we have to assume certain output, okay, to this particular Q. Okay, and then we have to go through this output sequence, how this output is going to be changed, right? So once we are applying the clock, okay, once we are applying the clock, and that time you will find that at the positive edge of the clock, okay, whenever the positive edge, this is your edge, okay, and this is your level, right? So normally it is a positive edge triggered. So whenever this edge will appear, the positive edge, okay, when it is going from 0 to 1, okay, that time this positive edge will appear, and that time this transition of the output is going to take place. So initially assume that if it is at the 0 0 0 0, okay, if this Q0 is also 0, Q1 and Q2 and Q3 all are 0 0, okay. So initially when it is 0 0, okay, here you can see that all these are 0 0, and whenever this first clock pulse will arrive at that stage, okay, this output will go to 1, because here you can see that when this Q is 0, Q bar will be 1, and this 1 will be connected to this D input, right? So whenever this 1 is connected to D input, when the next clock pulse will arrive, this 1 will be passing by this particular flip-flop, because it is a D flip-flop, and that's that time this output Q will become high. So here you can see that this output is actually becoming high at this particular positive clock pulse, right? So when this output Q will become high, you can here you can see that this Q bar will become 0, okay, because this will become high, and this Q bar will become 0. So again, you can see, because it is a asynchronous counter, okay, here you can see, because only the clock is connected to the first flip-flop, and rest of the flip-flops are actually driving by the previous flip-flop output. Okay, so it is actually we are driving this particular flip-flop by this Q bar. So when this Q bar will become like initially it was at 1 to 0, okay, it is going 1 to 0, because we have assumed that initially Q0 was 0, so this Q bar should be 1, and when this is making a transition from 0 to 1, that time this Q bar will be making a transition from 1 to 0. It means that we are actually getting a negative edge. Okay, we are actually getting a negative edge for Q bar. So when next clock pulse will arrive, at that time you can think of, because it is actually connected to your 0. Okay, Now it is actually Q bar is 0. So that time what happens, this D will be receiving a 0 as the input, and when the next clock edge will arrive, okay, at that time this output will become again 0. So here you can see that it is initially 1 and then it is becoming 0. Okay, this way it is going to be 0. And then at that time here you can assume that when this will become 0, okay, it is going from 1 to 0. Q bar is going to make a transition from 0 to 1. Okay, it will be making a transition from 0 to 1, that we have to understand. So when it is making a transition from 0 to 1, that time a positive edge will appear for this particular second flip-flop. And that time this is going to make a transition. Okay, remember that at that time only this particular transition is going to take place. So here you can see, because initially we have taken this as 0, so it was connected to 1. So this input to this second D flip-flop is again 1. So that time when this is making a transition, okay, whenever this is making a transition from 1 to 0, that time this Q1 will make a transition from 0 to 1. Okay, so at this point it is making a transition from 0 to 1. So this way it is making a transition. And again, in a similar fashion, you can assume that for all other flip-flops, when the transition will take place, right? So because it is asynchronous counter, the one by one, this flip-flop will make a transition, right? And this way you are going to get this kind of counting sequence, right? So this type of waveform you are going to observe if you connect this output to a oscilloscope. Fine. One important point that you have to make here is that in the case of binary ripple counter, okay, you can see that these output, okay, this clock is connected to this particular first flip-flop, okay, that is named as FF0, and it is going through FF1, FF2, and FF3, okay. So normally the output nearest to the clock, okay, because we are giving the clock to this first flip-flop, the output of this flip-flop is represented as Q0, okay. Then this output is Q1 and this output Q2 and this is your Q3, okay. So normally the output, okay, which is nearest to the clock is actually your LSB bit, okay. This is very important point that we have to take care. So while making the sequence, if you want to make the if you want to make means if you want to count the sequence, okay, you have to remember that this will be your LSB bit and this will be your MSB bit. So how to write this particular value? You have to write this value as Q3, Q2, Q1, Q0. Okay, this will be your output sequence that you have to remember. This will be making a more frequent changes. Okay, as our counting pulses will be arriving, okay, clock pulses will be arriving, and comparatively this will be make a little bit less frequent changes, okay, and the least frequent changes will be happened in the Q3 because it is your MSB bit. So that you can also observe from this, okay, because when you are writing this means 4-bit binary, if you take and if you make all the combinations, you will find that this is our LSB bit, and each at every clock pulses, okay, you will find that there is a transition for your LSB bit, okay, 0 1 0 1, okay. So for each and every clock pulses, okay, whenever we are arriving a next clock pulse 1 2 3 4, every time this LSB is making a change, okay, it is making a change, okay. You can see that its output is making a transition. So the same thing you can also observe from the Q0 waveform. At every clock pulse, it is making a transition. Okay, at 1, it is making a transition. Okay, again at 2, okay, the positive edge of the second clock pulse, again it is making a transition from 1 to 0. Again from 0 to 1, then again 1 to 0. This way it is making a transition, right? And similarly here again you can see that for the B2 it is 0 0 then 1 1. Okay, so again here you can observe that it is 0 0, then again it is 1 1, then again it is 0 0, then again it is 1 1. Similarly for B3 you can make this observation, 4 zeros and then 4 ones, again 4 zeros and 4 ones. The same thing you can observe here again. Okay, it is 0 0 0 0, 4 zeros, then again 1 1 1 1. This way again you can make the observation for your MSB bit. Okay, there will be a 8 zeros and again 8 ones. Okay, here you can again say this 8 zeros, okay, and then 8 ones. So this way, you will be having this particular output waveform. So normally what we can do is in this binary ripple counter while doing the experiment, either you can connect this to a particular LEDs, okay, and you can observe the sequence of glowing state of the LED, okay, when it is turning on and when it is turning off. That state you can observe. Or otherwise, you can connect this output to the 4-channel oscilloscope and you can observe the output waveform. Okay, there you can observe the output waveform, how these waveforms are actually changing. That way you can make the observations, right? Again, you can make one more thing, that either you can connect a certain display devices. Okay, I have already covered the 7-segment display, okay, using the BCD driver circuit. The same circuit you can again connect it to this particular output, and you will be able to see a few of them output counting sequence, like from 0 to 9 you will be able to observe. And then because ABCD is actually, in the case of BCD driver circuit, it will not be showing you that, okay? Or otherwise you can make a circuit that will be able to display the same thing, okay? Here again you can see this circuit, okay, using the this JK flip-flop, okay? So the same circuit you can also implement by having the JK flip-flop, right? So here we have this JK flip-flop. So binary ripple counter using the JK flip-flop you can make, okay? And here we are actually using this particular negative edge triggered flip-flop, okay? So that way you have to make this circuit, and then you will be able to observe the output. You remember that the JK flip-flop should be in the toggle mode. That you have to remember. Okay. And again, this Q0 will be your LSB bit, and this Q3 will be your MSB bit. Okay. You can take, you can just make the observation by just taking this Q0 like Q3, Q2, Q1, Q0 equals to 0, 0, 0, and then after applying the clock pulses, you will be able to draw this kind of waveform. A similar waveform you are going to observe. The only difference is that this transition will take place at negative edge of your input clock pulse. Okay, so that you have to remember. Fine. One more important point that we have to understand, that in this case, this binary ripple counter, this is a 4-bit up counter. Okay, what does it mean by up counter? Means the counting sequence will be in the forward direction. The meaning is that if we are having this, if we start the counter from the 0, 0, 0, that time it will be going through this particular sequence. Okay, it is going from 0, 0, 0 to 0, 0, 0, 1, then 0, 1, 0, 0, 1, 0, then 0, 0, 1, 1, and so on. So it is going to going through this particular counting sequence, and then it will be reaching up to this particular counting sequence 1, 1, 1, and again after that it will be reset to this 0, 0, 0, 0. Okay, and then again it will start recounting. So it is actually in the forward direction we are making this up counter. Okay, this way. Okay, there may be a chances that we can also make a like down counter. Okay, rather than making a up counter, you can also make a down counter. So at that time, this sequence will be like this. Okay, if you are starting with the 0, 0, 0, it will be going to this particular 1, 1, 1, then 1, 1, 1, 0, then again 1, 1, 0, 1, and so on. So this state will be, the state sequence will be like this, anti-clockwise, not clockwise. Okay, so that you remember. So that way we can make this changes. So how this down counter can be fabricated. So while making the down counter, here you can see that this clock that we have applied is actually applied from the Q output. Okay, and every next stage of your flip-flop, you can see that this is actually have been actually driving by the Q output of your previous flip-flop. If you connect this clock to the Q bar output, you will find that you will be able to easily implement the down counter. That I will be showing you just in a moment while going to this MultiSim software. Okay, so basically you have to remember what will be the day flip-flop, which IC we have to use, and which IC for JK flip-flop we have to use. What will be the internal pin diagram, that we have to remember. So we have to use this 74LS74 IC. Okay, this is our D flip-flop IC, and here you can see this internal pin diagram of our D flip-flop IC. So this flip-flop pin diagram you have to remember, because you have to make the connection onto the breadboard depending on this particular internal pin structure. Okay, here you can see that because in the D flip-flop we are having the D input, one input pin, okay, one clock pin. There will be another 2 pins which is known as preset and clear. Okay, so that you can see here. Okay, it is fourth number pin, which is your preset. Okay, and this is clear input, which is pin number 1. Okay, so input will be actually applied from the pin number 2 here, you can see, and this clock will be applied from the pin number 3. Okay, and then we have to take this output from pin number 5 and 6. These are your complemented output. Here you can see it is Q and this is your Q bar. Again, we have the ground pin, and then we are having the another D flip-flop, and these are the different pins. Okay, then we have to connect this VCC to a power supply. Okay, you must this is very must to connect this to a particular power supply of plus 5 volt. Okay, and then we have to make this ground, otherwise it will not work. Okay, that we have to remember. So this pin diagram is very important. You have to remember this pin diagram. And while making the connection, you have to remember that this clear and PR. Okay, this preset, it has to be connected to positive voltage power supply. Okay, positive side. Okay, it should be connected to logic 1. Okay, it should not be connected to logic 0, otherwise this inputs will be activated and the output will be controlled by this input conditions. Okay, so that you have to remember. Again, you can see this JK flip-flop. So this is the internal pin diagram of the JK flip-flop. You can go through it. This particular IC number is 74LS76. Okay, that you have to use. And here you can see that again we are having the two different flip-flops. Okay, and this is your inputs. Okay, JK. Here it is the fourth number pin is 1J. Okay, means your first flip-flop input. Okay, and this is your K input. Okay, which is connected from the pin number 16. Similarly, you can see all these outputs. Okay, you have to remember this. You have to follow this internal pin diagram properly. Otherwise, you won't be able to get the output. One important point that you have to remember is about this 74LS76 JK flip-flop IC is that here the ground is actually pin number 13. Okay, that you can see. The ground is your pin number 13, and your VCC is actually connected to pin number 5. That we have to remember. Okay, because in the case of all other ICs, you will mostly find that the pin number 7 is connected to ground and pin number 14 is normally connected to VCC power supply. But here it is a 16 pin IC. Okay, and therefore this convention a little bit changed. That we have to remember, and then you have to make the connection accordingly. One more important point that you have to remember while implementing the circuit onto the breadboard is that you have to give the clock pulses by using the TTL clock. Okay, so normally in the laboratory you will be having a different kind of waveform generator. So normally in the waveform generator you will find that this option. Okay, normally in the waveform generators there will be a written like TTL or CMOS output. So from that TTL or CMOS output, you have to make the connection. Okay, this is your waveform generator actually. And from the waveform generator, you have to connect this to a particular circuit. Okay, at the clock input, I mean to say. And there you have to apply the clock frequency of a means clock pulse of a certain frequency and of a certain duty cycle. You can control the duty cycle by having a duty cycle knob. Similarly, in your laboratory, you have to find out what kind of facilities are available and what kind of waveform generator that you are having. You must be having a certain option to give the clock pulses. Okay, so you have to remember you have to use the TTL clock. It will be giving you a stable frequency and a stable amplitude output. Okay, so that you have to see. So now I'm just going back to this MultiSim software. Okay, and then we will be seeing how the same circuit can be implemented. So these are the different components that we have to use. Okay, we have to use the D flip-flop, we have to use the JK flip-flop to implement the counter circuit. So normally in the MultiSim, you will find that we are having this discrete, a single JK flip-flop component, which is available in the case of MultiSim. But normally in your laboratory, you will not be finding this particular means single component JK flip-flop. Okay, only single JK flip-flop is not available, but it is a dual flip-flop will be available in the form of ICs. Okay, 74LS74 ICs will be available. Okay, and this is your IC that will be available in the laboratory, that you have to remember. And based on this internal pin diagram, you have to make the connection. Similarly, you can use 74LS76. Okay, so this is the IC of JK flip-flop that you can also use for implementing of the circuit. In this case, on MultiSim, actually, I'm using this discrete IC, this discrete flip-flop. Okay, to make the connection more easy to. Okay, there will be no power supply and all. So just I'm using this one to demonstrate the circuit. Otherwise, onto the breadboard, you have to use this only because it is not available in the case of breadboard or hardware cases. Okay, in the hardware, we are not having this discrete flip-flops. Okay, we are having the ICs in which there will be two flip-flops available. Okay. So now here you can see this is our counter circuit. Okay, I have already made this circuit. Okay, and here you can see this circuit, the same diagram I have implemented that I have shown you. Okay, I have just shown you in this circuit diagram. Okay, this circuit diagram I have implemented. Okay, this is your D flip flop. This is first clock is connected to the first flip flop, and then this output is connected to the input. Again, this output is connected to this inputs. Okay, and so on, and then we are connecting the this Q bar is connected to the clock input of your next stage of your flip flop. The same thing I have implemented that you can observe here. Okay, these are the flip flops. The clock is connected over here, then this output is connected to this input. Okay, and so on. You here again you can observe this. Okay, and this output is connected to the clock input. Okay, that you can see. You can verify this output. Okay, now here you can see, as I said, that this preset and this clear input should be connected to logic high. Okay, it should be connected to a positive side of your power supply, so that I have already connected over here. Okay, this is mandatory to connect it, otherwise it will not work. Okay, that you have to remember. Otherwise we are going to get a wrong output. Okay, or even the output will not appear. Okay, so you have to see this. Okay, you have to connect it with the positive side of your battery. Okay, so this way you have to make the connection. So I have all these flip flops have been connected to this particular positive side of the battery. So this way you have to make the connection. For observing the output, what I have done is I have connected these LEDs. Okay, here you can see these LEDs I have connected, and I also have connected, I have taken this 4-channel oscilloscope, and then I have connected this all outputs to this oscilloscope. Okay, there are total 4 outputs, and remember that this will be your LSB bit. Okay, this output will be your LSB bit, and this output will be your MSB bit. Okay, here I have taken the digital clock, and here you can control the frequencies. Okay, I have just made it this 10 kilohertz. Okay, that I have make it 10 kilohertz. You can make it more. Okay, no problem. You can just let me make it to 50 hertz. Okay, normally while doing the experiment, okay, in the laboratory we have to choose 10 kilohertz or 1 kilohertz. That will be able to means that will be sufficient to get the output. Here I'm just making 50 hertz, but normally when you perform onto the breadboard, you have to make it 1 kilohertz or more than that. Okay, 10 kilohertz, that will be sufficient to get the output. So if you execute the circuit, okay, you can observe this sequence. Okay, we can see this LED is actually glowing in a particular fashion. Okay, so as you can see, this is your LSB bit, so it will be making more rapid transitions. So LED will be switching on and switching off at a rapid pace. Okay, as compared to this LED. And here again you can see that this LED is also making a transition, but that transition is not so frequent. And you can see this is your MSB bit. Okay, so to observe whether we are getting the same sequence or not, you can just click this one. Okay, and you can observe this output waveform, right? So here you can see, let me stop it, and then you can try to observe this output. Okay, so here you can see these outputs, right? This is your LSB bit. Okay, this is your LSB bit. This is your MSB bit. Okay, this is your MSB, this is your LSB bit. Fine. So now you can see that if you see at this stage, okay, at this time, here you can say this is your 0 0 0 0. So let me count it like because this is your MSB bit, this is your LSB bit. So again you can just go back to this output waveform. This is your MSB bit, this is your LSB bit. Okay, so initially we have started with the 0 0 0 0. Okay, then it is going to 0 0 0 1, then again 0 0 1 0, then again you can see 0 0 1 1. The same way you can observe the output here again. Okay, you can see this output. You'll be able to understand this out. Okay, so this is our MSB bit. This is your 0 0 0 and 0. Okay, then again at the next clock pulse 0 0 0, this is becoming 1. Okay, similarly, here you can see this is 0, 0, then this is 1, this is 0. Okay, then again 0, 0, this is 1, 1. Again, you can see it is 0, 0, sorry, 0, 1, 0, 0. Okay, similarly, it is 0, 1, 0, then again it is 1. Okay, so this way you can make this all, you can count all the sequence. Okay, here again you can see the last counting sequence is last state will be your 1 1 1 and 1, and again it is making transition up, means it is going again back to 0 0. Okay, so here again you can observe this is 0 0 0 0. Okay, so this way you will be able to observe this particular output. Okay, so now you can see the same output. Okay, we can again see the same counter, okay, ripple counter, by using the JK flip-flop. Okay, so I have taken the JK flip-flop. Okay, I have connected to this particular first flip-flop is connected to the 50 hertz clock, and then we have to connect this clear and this preset to 1. That I have already made this connection. Here you can see. Okay, and then this circuit I have actually implemented. Okay, you can see this circuit. Okay, this Q is actually connected to the clock input of our next stage JK flip-flop. So this I have already made this connection. Okay, you can observe this. One more thing that I have done is to just observe the counting sequence. What I have done is I have actually connected another BCD driver circuit, and here I have connected the 7-segment display circuit. Okay, so that will be able to show you certain counting sequence. Okay, because here when the LEDs are glowing very fastly, we are not able to observe what will be the outputs. Okay, so here you can see all these connections. Okay, you will be able to easily implement this circuit onto the multisim or even onto the breadboard. Okay, so here you can see this connection. So in the multisim, we are having this option of DCD hex. Okay, display circuit. So that will be directly, that can be directly connected, and we will be able to observe all the output sequence. Okay, but normally this is not available in the hardware form, but this 7-segment display is available. Normally in the laboratories, we are actually having this 7-segment display, so that you can use, and you can observe the output sequence also. Rather than connecting this BCD driver, what you can do is you can actually make a truth table. Okay, and then you can design a circuit. Okay, that will be able to display all the output sequences. Okay, so now you let's try to see, because it is a up counter, binary up counter. Okay, using the JK flip flop, here you can observe this output sequence. Okay, see, this is 0, then this is 1, this is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and again it is going back to 0. So this way you are actually going to get this out. Okay, this way you are going to get this out. So this ABCD is nothing but your, because it is a hex display. Okay, so this 10 will be represented by A, 11 will be represented by B, and so on. Okay, so now you can see if I want to change the down counter. Okay, how to make a down counter? You can just stop it, and as I said that if you change this clock input. Okay, so right now we are actually deriving this next stage flip flop by using the Q. Okay, if you connect this to Q bar, okay, all this flip flop has to be actually connected to Q bar, and that time you will be able to observe that the counting sequence would be changed. Okay, so just let me make this changes. Okay, if you just connect this one, okay, if you make this little changes, okay, in the circuit, okay, you'll be able to see this change. Okay, so let me just make this changes. So now I have connected to this Q bar output. Okay, so now if you execute the circuit, you will be able to see this sequence. Okay, you observe this sequence: F, D, C, then B, then A, then 9, 8, 7, 6, 5, 4, 3, 2, 1, and so on. Okay. So normally, because here we have made this clock pulses, which is of 50 hertz. If you increase this frequency, okay, obviously observation will become very tough. Okay, we will not be able to observe it so smoothly. If you run it, okay, if you execute it, it will make transition so fast, you will not be able to observe it properly. Okay, right now we are able to see it, but in some cases, okay, if you increase it further, okay, that counting will be taking place at a very rapid pace. Okay, that time it will not be able to. Normally, in the case of breadboard and laboratory, what we do is we are connecting the this oscilloscope to observe the output. Okay, so again, you can see this waveforms how it is changing. So I hope you must have understood how to implement the counter circuit. Okay, so try to implement the same onto your breadboard. Okay, and also those who are having the MultiSim software, you can make this circuit and you can observe the output sequence. If you have any further doubt, you can drop me a message in the comment box. I will be making clarification if you have any further doubt. So thank you for watching this video. So please stay connected with the channel. I will be coming up with more videos. So stay tuned with this particular channel. And thank you for watching this video.